Hey everyone, welcome back to my channel. Today we're exploring one of the most powerful uses of databases, geospatial analysis using PostgresSQL with the PostGIS extension. If you've ever wondered how apps find the nearest restaurant, detect whether a building falls in a flood zone, or link property data with geographic boundaries, this video is for you. We'll be running real SQL queries using PostGIS to explore how spatial data is stored, how to perform spatial joins, and how these queries answer real-world questions using geographic relationship. So let's get started. PostgresSQL is a powerful relational database, but by default it does not know or understands how to calculate space. That's where PostGIS comes in. PostGIS adds support for geographic objects, enabling location queries to be run in SQL. It stores spatial data like points, lines, and polygons. Under the hood, it uses special data types like geometry or geography, which allows us to run spatial calculations directly in the database. Now let's see this in action. So I've already preloaded my PG admin interface and I have a number of servers. For this demonstration, we're going to be using the local server, and in my local server, I have a mineral property database. So I've preloaded the layers in my mineral property database, which is in my public schema. So as I mentioned earlier, the PostGIS extension allows the support of geographic data in the forms of points, lines, and polygons. So for this data set, I have all my layers are polygon layers. So let's actually view the contents of these layers. This can be done in the database by simply highlighting the layer, and then you right click and go to view edit, and you can view the first 100 rows. So this allows you to visualize the contents of the layer. So as you can see in my Amerindian area layer, I have a number of columns and I have a number of rows. So let's do the same for the small scale area. So again, you select and you right click and go to view edit the first 100 rows. So once again, you can visualize the contents of the layer in the database. Now there is this little icon at the top of my geom column that if I hit on it, it actually shows me what the data would look like in a mapping software. So this is what the contents in my small scale layer looks like. So I think that's pretty nifty. Now you can get back to your table by simply clicking on the output, the data output. So now that we've examined the contents of the layers, we're ready to build our spatial query. So we'll head back to our main window and we're going to hit on the query tool. This is going to open up a new window that will allow us to type our SQL query. So the query we'll be running today is a containment query. The objective of this query is to identify all the small scale properties that are completely within a particular Amerindian area. So let's dive in. So first I'm going to start off by entering the select function. And I'm going to indicate a alias for my Amerindian area layer. So I'm going to say area name because there is a name column in my Amerindian area layer. And I'm going to say as my Amerindian area. Next, I'm going to list all the columns from the small scale table that I want to be added to my newly filtered data. So I'm going to assign the alias as claim, and I'm going to be pulling the claim number column, and it's going to retain the same name. I'm also going to be pulling the claim name column. It will also retain the same name. I'm going to pull the claim holder. because this is important, and it's important to know who owns the property in the Amerindian area. And in my newly filtered data set, I'm going to spell out the word owner. So if you may have noticed, in the first instance, the word owner is not completely spelled out. This is because if I go back to my small scale layer, you would notice that the column claim owner, the word owner is not completely spelled out. This is important because I'm telling the syntax to pull information from that column. So I have to retain the same spelling as it's stated in that layer. So now I'm going to also retain the claim status. However, this is going to be renamed status in the filter dataset. So I have identified all the columns that I want to be added to my filter dataset. I'm going to now insert my from layer. So because we'll be pulling, our main table is going to be the Amerindian area is what it's going to be compared against. I'm going to say from, and now I'm going to go back to my Amerindian area tab and simply copy the path for that layer. This is to avoid any incorrect spellings or error when I'm running my script. And now I'm going to insert my join, which is going to be my small scale layer. And again, I'm simply copying and pasting to avoid incorrect spellings as the alias, which is claims. So now that I've established my layers, I'm going to insert my function. So I'm going to say on, and my spatial type is contains. So I'm going to type contains. And I'm going to insert the alias from my Amerindian area, but I'm pulling from my geom column, and I'm going to insert my alias from my small scale and also pulling from my geom column. It is important to note, guys, whenever performing any spatial queries, spatial joins, that the layer should be in the same reference coordinate system or you will get errors. So because I do not want to filter the entire Amerindian area but just a specific Amerindian area, I'm going to enter the where function, and I'm going to say where area, and in my Amerindian area there is a column called name, and I'm going to say it has to be equal to a particular Amerindian area. So I'm going to say Iseneru. Now once that is completed, I'm simply going to close my query and hit execute. And there you go, guys. It's successfully run with a total query time of 503 milliseconds with 42 records affected. So let's examine our outputs. So we have 5 columns as we specifically stated at the beginning of our query. We have the Amerindian area, we have the claim number, the claim name, the claim owner, and the claim status. So our query was successful, and it provides insight into the number of claims that are within this particular Amerindian area. So let's say we wanted to do multiple Amerindian areas. That's fairly simple. We'll just remove the equal sign and we're going to insert the in function. We're going to open the brackets, and now we're going to enter the name of the other Amerindian area. So I will say Jawala. Once that is completed, I'm going to close my bracket and I'm going to hit execute. So there you go, guys. It ran pretty quickly with 466 within 466 milliseconds, and it returned 74 rows. So let's examine this output. So now we have the same columns, but if I continue scrolling, you will see that in my Amerindian area column, I'm moving away from the word Jawala and I'm entering into the word Isenro. So this simply put is that I can see the number of claims and what claims are within Jawala, and I can also see the number of claims and what claims are within Isenro. So I think this was a pretty cool join, and it provides information on land use and environment monitoring and so forth. So spatial joins are pretty good, guys. But let's take a look at the data. We can see in the status column that we have properties that are active, we have some that are null and void, some that are abandoned. So let's say we just wanted those properties that are active, the properties that are active that are within these area. So how do we add that? This is how we add that. We simply add a new line to our SQL query and we're going to say and we're going to specify our claim status, our alias for the claim layer and the claim status column from the small scale layer, and we're going to say this to be equal to the word active, and let's run. And there you go, guys. It successfully ran within 994 milliseconds and now it returned 39 rows. So if we scroll through the data, we will see in our status column, it's only depicting all the active claims that are within Joala and Isinero. So there you go, guys, a spatial join conducted in the PostgresSQL Postgis extension. So it was very fast with runtimes in less than a second, so that was pretty cool. So if you've made it this far, then you've seen how powerful geospatial database can be. With PostGIS, we can run PostgresSQL in a location-aware engine that powers real-world decision. If you're working with maps, infrastructure, or any data that moves through space, you'll need to be using geospatial SQL. If you like this video, please give it a thumbs up. See you next time, guys. Bye.